Okay, let's pick up where we left off. So we just calculated that there are billions and billions of protons flowing around. So when you picture even just a simple circuit with a battery and a light bulb, 42 milliamps is not a tremendous amount of current, but it's not a small amount of current. So there are just billions and billions of things flowing around inside. And yes, we're going to pretend that it's the protons flowing around inside, even though we know in our heart of hearts it's actually electrons. Okay, so I'm going to introduce another analogy here to help you visualize what's happening. This one is going to be a plumbing analogy. So I want you to imagine all the plumbing in a large building, such as South Brunswick High School. And first of all, what would represent the charges in a building like this? Well, hopefully you're saying that's the water, right? So billions and billions of water molecules flowing, billions and billions of charges flowing. What would represent the wires? Well, that would have to be the pipes, right? The water flows through the pipes, the charges flow through the wires. All right, here's a tougher one. What represents the battery? A lot of students probably don't know this one, but you have to think, what does the battery do? Well, the battery pushes charge around, right? So what pushes the water around inside plumbing pipes? That's actually called a pump, right? The pump provides like a pressure to push the water around. So that's what sort of the battery does. It sort of pushes the charge around, providing pressure. All right, now we're going to introduce a term called resistance. So what could offer resistance? So let's say you're in your house and you wake up in the morning and you want to shock yourself awake. So you get in the shower and you turn the water on, hoping a full force stream of water is going to hit you in the face and wake you up, and just a trickle comes out. Obviously, there's something inside the pipe, something clogging it up. Now, we don't need to get into the details of what's actually clogging it up. You probably don't want to know what's clogging it up, but there's something there limiting the flow of the water. Well, that's an analogy for what happens in circuits as well. There's something offering resistance. Now, also, when you picture the water flowing through a pipe, it'd be really nice if the water flows in a nice, what's called a streamlined way, all nice and smooth. But that doesn't really happen. The water molecules bump into each other and swirl around, and they hit the sides of the pipe. It's actually rather chaotic. There's a name for this that's often associated with airflow, usually around the wings of airplanes. So you would know this as turbulence, right? So as water flows through a pipe, there's a turbulent flow. Well, that's really a good model for what's happening with the charges and why there's this resistance. Okay, so let's talk about this electrical resistance. And we have a symbol here that makes sense, capital R. Capital R stands for resistance. We like that. None of this I for current business. And we define resistance as how much a material limits the flow of charge. And of course, the flow of charge is current. Right? So just like the clog in the pipe limits the flow of water, something about the material limits the flow of charge. It resists. It holds it back. It limits how much charge flows. Why does it happen? Well, just like we said, it results in the charges bumping into each other. This turbulent flow. Resistance is a scalar quantity, and some of you may know the units for resistance is the ohm, OHM. That's the Greek letter omega, but we say it's the ohm. Okay, so just like the capacitor in a circuit has capacitance, the resistor in a circuit has resistance. We'll make sure we're using our terms properly. Right? So the resistor is the thing with resistance. We define it as any device that transforms electric potential energy into something else, something that's useful. So before, we were talking about putting a light bulb in a circuit with a battery. Well, prime example would be a light bulb. But really, all these other things here are resistors as well. So you're constantly living with resistors. You're using resistors all the time. Basically, it's anything that uses electricity, right? Anything you plug in, anything that uses a battery, it's taking the energy stored in a battery and transforming it into something useful. Light and heat for a light bulb, light for a calculator, light and sound for a cell phone, light and sound for a TV, so on and so forth. So you're constantly using resistors. In the lab that we're going to be doing, we're going to be setting up circuits that look something like this. And so here I have a very simple circuit where this is the lab volt. That's an adjustable source of voltage, just like a battery. Here's a wire leading to a meter that's going to be measuring the current. And this leads over here to a resistor that's in this Lego block looking thing. And then the wire leads back to the battery. And I've got another meter here connected to the resistor to measure its voltage. Here's a close-up look at the resistor. You can see it's rated at 5 ohms. So it's a 5 ohm resistor. And it's not really the Lego block looking thing. It's actually this gray cylinder inside. That's the resistor. Okay, so the idea is that in class I'd set this up and we would take some data for it. And so we're going to do the same thing here. So I want you in your notes to set up a data chart, current and voltage. And I've done the experiments, I've taken pictures of it, so you know I'm not just making up the data. All right, so when there's no voltage across the resistor, there's no current either. So it starts at 0, 0, so you can put 0 in both columns. This one's measuring the current, this one's measuring the voltage. Right, so it starts at 0, 0. And then we're going to go up in increments of 0.1 amps. So when this is at 0.1 amps, we see there's 0.5 volts across the resistor. So you put that in the chart. And the next couple of photographs are just going to keep going up by 0.1 amps. So here's 0.2 amps. And record the voltage. And 0.3 amps. And record the voltage. We're going to go up to 0.4 amps next. Take a guess where you think it's going to be. Were you right? Oh, you're probably real close, right? You probably guessed 2 volts, but hey, it's not. It's 1.9, but that's okay. This is the real world. Sometimes things don't go exactly as planned, and that's fine. Nothing wrong with that whatsoever. All right, so here's our entire data chart. And now I want you to sketch out a graph, what would look like when we plotted this data. If you really want to take the time to actually plot it out, okay, but really you should be able to see the pattern pretty clearly, even though there's a minor deviation at the very end. Clearly, what sort of relationship is this? Well, I hope you see it's a linear function, right? So yes, it's going to be a straight line. Even when we plot the data, it might not be a perfect straight line, but you can see it's pretty much linear. What do we do with a straight line? Well, of course, we find the slope. And so here, what would the slope represent? Well, it's going to be voltage over current, right? Delta V over I. And just look at the numbers. You don't have to actually find the slope. Just look at the ratio. It's pretty much a constant ratio, which is about 5, right? It's a 5-to-1 ratio. What else was 5 that I just showed you? Oh, right, that was the resistance on the resistor. So here we see our equation for resistance. Resistance is voltage over current. This also shows the relationship among the units, right? 1 volt per amp is 1 ohm. This is the definition of the ohm, 1 volt per amp. Now, I'm not going to box this in just yet, because traditionally this is solved for delta V. So that's the way I want us to write it, is delta V equals IR. We'll box it in. And this was first discovered by Mr. Ohm. This is Ohm's law. So I'm not really sure if it's a historical reason why we write it this way, or maybe writing this way highlights the linearity of the function. This is on the y, and this is on the x, and this is the slope. Although not all devices will have a linear function. That's only when the resistance is constant. That would make a linear graph here. So the resistor we used in the circuit there is called ohmic, because it has a constant resistance. It follows Ohm's law perfectly. Not all devices are ohmic. In fact, very few resistors are ohmic. So again, the charges are bumping around inside the resistor that offers resistance, but anywhere charges bump around, there's going to be some resistance. That includes the wires. So let's talk about the resistance of a wire. And so here, I'll introduce another analogy. I introduce a lot of different analogies because one analogy is going to click with one student, a different analogy is going to click with a different student, so it's just different ways of visualizing it. So this analogy is about students in the hallways. So imagine it's the end of the school day, the bell rings, and all the students pour into the hallways. They're all trying to get places. A lot of students are trying to get to their buses. A lot of hustle and bustle. It's very chaotic, just like the charge is moving around inside the wires, right? And you've got to sort of dodge and weave, and what always happens is clumps of students forms at the lockers, right? There's these clumps of students where maybe the students they can take their time. Maybe they've got a club or activity to go to. They don't have to rush to catch a bus. Or maybe it's the seniors who can mosey out to their cars. They're not in a big rush either. But people who have places to go to get to their bus, as you go through the hall, you've got to dodge and weave around these clumps of students that gather at the lockers. So imagine 2 hallways. There's a long hallway with lots of lockers and a shorter hallway with fewer lockers. Which one offers more chances for those clumps to form around lockers? Well, hopefully you say it's the longer hallway, right? Longer hallway, more lockers, more opportunities for those clumps to form. And that's an analogy of what happens in a wire as well. A longer wire offers more resistance. So what really happens is, as you're imagining all the protons flowing around inside the wire, some of the protons don't participate. Some of them stay in their nucleus. Now, we know, of course, all the protons stay in the nuclei, but we're pretending that the protons flow, right? So some of the protons don't participate. They're like the students who clump together at the lockers, and the ones that do participate have to dodge around them. So more chances for that to happen, more resistance, longer wire. Okay, so where in the building is the worst for traffic? You know, it's the bridge, right? The bridge is the worst. It's just too narrow, right? And so a narrow wire also offers more resistance. Whoever built the bridge, I'm sure it's structurally sound, but it doesn't account for all the students that have to pass through. And so in a wire, when there's not a lot of space for the charges to flow, well, they bump into each other more. That offers more resistance. Of course, resistance in a wire also depends on what the wire is made out of. So here's going to be the equation for resistance of a wire. There's the length of the wire. Longer wire, more resistance. This is the area, the cross-section area of the wire. So a narrow area makes a larger resistance. And this term here describes something about the material itself. Let's box this in. Okay, so let's define our terms here. Capital L is the length of the wire, given in units of meters, of course. Capital A, again, is the cross-sectional area of the wire, given in units of meters squared, of course. And then we have this symbol. Now, this symbol is not a P. This is a Greek letter. And we've actually seen it before a long, long time ago, so you probably don't remember. And we used it for something completely different. But that is the Greek letter rho. So it sort of looks like a curvy P. But don't say P because you can be very, very confused. So don't call it P. All right, so rho here stands for resistivity. It is a property of the materials itself. Something that tells you about how resistive it is. All right, so pause the video here and figure out what units resistivity must be measured in. Hopefully you came up with ohm meters, right? If the resistance has to be in ohms and length is in meters and area is in meters squared, an ohms times a meter, that's going to give the proper units for resistivity to return all the units that need to be done. Resistivity is also a scalar quantity. I think I forgot to put that here in the PowerPoint. Okay, so, let's figure out here what sort of results we'd get by putting different materials there. What would you know about a material that's very resistive? What sort of material would that be? Something that resists the flow of charge, that would probably be an insulator, right? A conductor would have a low resistivity. So here is a table that's actually taken straight out of your textbook of different resistivities given in ohm meters. At the top are some of our best conductors, right? These are the 3 top conductors we mentioned earlier in the year. And look at their resistivities. Those are tiny, tiny numbers. Here we're increasing resistivity as we go down the line here. So here are some conductors, just maybe not as great conductors. Sorry about that, I accidentally clicked ahead on the PowerPoint. So I was just trying to show that here we get to carbon, which is a semi-metal, right? It's a non-metal, and the resistivity jumps up, although still it's pretty low. Carbon can conduct. Now we get to germanium. That's a semi-metal, and that has a very large resistivity compared to these other ones, and now it's just getting larger and larger. Look, glass, we know that's a good insulator. Rubber, definitely a good insulator. We're talking about 10 to the 13th, right? And so really good insulators have very high resistivity. That should make sense. Okay, now we're going to go ahead and try problem 8. So pause the video. I'll leave this slide up so you can have the resistivity of copper showing, because you need that for problem 8. Okay, so we're using R equals rho L over A. What area are we talking about? Well, imagine it's a cross-section of a wire. And what shape is that? Well, that's a circle. So we're talking about pi r squared. Here's the resistivity of copper given by the chart you just saw. And of course, the length was in centimeters, so converting to meters. And the diameter was given, right? Not the radius, the diameter. So if you need to fix that, make sure you pause the video and do that. And the diameter was given in millimeters, right? So you have to make sure you convert that as well. So in the end, we get this as the resistance, although that's not a very useful number. So let's put this in milliohms, 0.346 milliohms. And that's a really small number, which is to be expected, right? A copper wire should have a very small resistance. It's copper, right? It should be a good conductor. We use it in wires all the time.